Welcome back, students. In this lecture, we'll start with Unit 1 of Structural Analysis 2 as per the RTU syllabus. Okay, so in this lecture, we are going to take the topic strain energy due to axial loading. So, first of all, we have to understand what strain energy. Okay, so when an elastic body is subjected to any kind of load, the body will deform because it is an elastic body. And during this deformation, some work is done upon the body, which means that some of the energy is stored in the body during this deformation process. So this particular energy which is stored in the body is called as strain energy, and this energy is stored on account of the restoring force developed on the body, right? So we can say that this particular strain energy or the energy stored in the body within elastic limit is called as resilience, okay, which is term denoted by U, and its value is going to be sigma square by 2 E multiplied by V, which is volume, and sigma is stress. Okay, we'll see the derivation later how it came. Okay, but at this point it is worth to notice what was our stress, right? So usually we make a mistake while defining stress. We usually say stress is force per unit area, okay, but actually stress is actually the restoring force divided by area of the cross section, right? So the term restoring force R or resisting force R is important. Okay, now let's see some more terms related to strain energy, which is proof resilience. So proof resilience is the maximum strain energy which can be stored in a body, okay, is called as proof resilience. Okay, so beyond this particular value a body cannot take strain any energy. Okay, so proof resilience indirectly indicates the capacity of the body to bear shocks. Okay, so proof resilience is denoted by UP is equal to sigma E, where sigma E is nothing but the stress at the elastic limit. Okay, sigma E square by 2E multiplied by volume. Okay, and the proof resilience per unit volume is called as modulus of resilience, and it is denoted by UN. Okay, now let's see strain due to different types of loading. Okay, so first of all we'll take up strain due to gradually applied axial load. Okay, so let us consider a bar of length L. It is having cross section of A, and it is applied with a axial force P. It is free at one end and it is fixed at the other end, which means that when a force of P is applied at the free end, the body will extend by delta L. So deformation is delta L. Okay, and let's say that the axial stress induced by the bar is sigma, and the modulus of velocity of the bar, which is a material property, is E. Okay, now so whenever the load is applied axially, gradually the load will increase from 0 to a maximum load of P, right? And during this the deformation will also elongate proportionally. So the load versus deformation graph will be an inclined straight line as shown here. Okay, and as such whenever the load is given to the body, there is a small deformation happening, delta L is happening, right? So this delta L will give rise to a small strain, which will again give rise to a stress, which is a restoring force, right? This stress integrated over the entire area will give a resistance, right? So if we try to plot the resistance versus deformation graph also, we can see that The resistance also increases gradually as the deformation increases from 0 to R. Fine. So what was sigma? Sigma is nothing but R by area, right? So our aim is to find out what is the value of sigma whenever what is stress induced in an axially loaded bar. Okay, so in order to find out, we can see that work done on the bar is nothing but the area under the load versus deformation curve. Okay, so which is half into P into delta L. Okay, so that was written here. Now the work stored in the bar, which is nothing but our strain energy. Okay, so strain energy is equal to the area under the resistance versus deformation graph. Okay, so this is again a triangle, which means the area is equal to half into base into height, which is half into delta L into R, right? So now we can say that what was R? R is stress into area. Resistance is stress multiplied by area, right? So we'll keep that aside. So now we have work done and work stored, which should be equal to each other, right? So we can say that half P into delta is equal to half into sigma into A into delta L. The delta L and delta L get cancelled, and half gets cancelled each other, which means that P is equal to sigma into A, which indeed means sigma is equal to P by A. Okay, so this is a well-known facts already known to you, right? So stress developed in a bar due to gradually applied load is P by A. Okay, now we already have what is strain energy, right? It is area under the resistant deformation curve. So strain is equal to half into R into delta N, right? R can be rewritten as sigma multiplied by A. So R is written as sigma multiplied by A, and instead of delta L, we can say what is delta L? Epsilon into L, right? Because epsilon strain is equal to change in divided by original length, which means that delta L is equal to E into L. So that is written, instead of delta L we have written E into L, epsilon into L, right? Again, what is epsilon? Strain is, according to Hooke's law, strain is stress by E, right? Or E is equal to stress by strain. From that you can get strain is equal to stress by E. Okay, so if you do this calculation, we have U is equal to sigma square by 2E into A into L. Then now we'll get what is A into L. A into L is nothing but our volume, right? So we can say that the expression for strain energy U is equal to sigma square divided by 2E into V. Okay, so as long as the resistance versus deformation curve is a triangle, the strain energy will be always U is equal to sigma square by 2E multiplied by volume, right? So this is something to be remembered. Got it? Let's see what happens when the load is applied suddenly. Okay, all the other credentials remain the same. The bar is of length L and area A. It is having a motor's velocity of E. Then one end is fixed and the other end is free. So when at the free end, here the load is applied suddenly. So when load is applied suddenly, the load is 0 at t is equal to 0 second, as well as when the final deformation also happens. Okay, so the load doesn't increase from 0 to a maximum of p. Instead, the load is p at beginning as well as at the final instant during the deformation. Okay, so we have a rectangular load versus deformation curve. Okay, however, the resistance doesn't increases normally from 0 to r. At time t equals 0, the resistance is 0, and it gradually increases up to a maximum value of r. Okay, so that is delta. That is when deformation is the final deformation, delta L, right? So the energy work done on the bar is equal to area under the load deformation curve, which is area of a triangle, area of a rectangle, which is P into delta L, and work stored in the bar is nothing but area under the load deformation curve, which is half into R into L. Okay, so half into R into delta L. Okay, R is again sigma multiplied by A, so we'll leave that. Now we have to equate work done equal to work stored, which means that P into delta is equal to half into sigma into A into delta. Okay, delta L and delta L get cancelled. We have sigma is equal to 2P by A. Now this is also important. Okay, so here also we can see that when load is applied suddenly, the instantaneous stress developed in the bar is twice the value of the stress intensity produced when load of same magnitude was applied gradually, right? When P was applied gradually, the sigma value was P by A. But when P is applied suddenly, the instantaneous stress or the maximum stress is going to be 2 times P by A. Okay, so this is an important concurrence. Here also, if we check work done or work stored in the bar or strain energy is having the same expression as previous case, half into R into L, which will be again equated to sigma square by 2E multiplied by volume. Okay, however, only this value of sigma is twice that of the previous. This should be kept in mind. Now let's see what happens due to impact loading. Okay, so impact loading is actually a special case of sudden loading. However, the load has already done some work before it hits the object or body, right? So one example is a falling object or falling weight on a body. Okay, so here we have an example. Here we have a cantilever bar of length L, and from above hit a mass, a body of mass M fall through a height of h. So the body will be having a weight of m into g, which is denoted by p. Okay, it falls through a distance of h, which means that there is some energy obtained by the body before it hits the bar, right? So there is a potential energy which is equal to p into h, right? So now that is important. Okay, and when it hits the body, the bar will undergo a small deformation delta L, right? So in this case, the load deformation case diagram will look something like this, right? The load travels by a distance of h and L, and during all this instant the value of P is same, right? So the load versus deformation curve will be something like a rectangle again. Okay, so we have two rectangles here, one of base h, another of base delta L. This is h is due to fall and delta L is due to deformation. Okay, now the body itself is knowing about this particular work done only when it hits the bar, only when the weight hits the bar. So it is not conscious of what is h, right? So the resistance will start from 0 to a maximum of r. Okay, from 0 deformation to a maximum deformation of delta L. So here also the resistance increases from 0 to r linearly. Okay, so this is our resistance deformation graph. Now we can see usually what is work done on the bar, which is equal to area under the load deformation curve, which is equal to P multiplied by H plus delta L. Okay, what is delta L? Delta L is sigma L by E, right? We have epsilon is equal to we have epsilon is equal to delta L divided by L. We also know that epsilon is sigma by E, right? So from this expression we can have what is delta L. Delta L is sigma L by E. Okay, so work done on the bar is P into H plus delta L. Delta L is sigma L by E, and work done in the bar is equal to half into delta L multiplied by R, which is area of this triangle, right? So this is again strain energy, which is we already know, which is final value is sigma square by 2E into E. Okay, now we'll derive. So work done should be equal to work stored. We have the previous equation, so we substitute it to here already, right? We'll expand this, we get something like this. Instead of V, we wrote A into L. Okay, we have something in sigma square. We have one expression in sigma, and we have one expression which is pH, which is a constant, right? So substituting, we get an expression something like this. So if we check this is a quadratic equation, so we can solve the quadratic equation, or you can use the method followed here also. Here we have used adding and squaring method. Okay, also you can use a quadratic equation method also, because this is sigma square, so A is equal to 1. This is sigma, which means that B is equal to minus 2p by A, and this is C, which means that which is a constant, which means that is equal to C is equal to minus 2EPH by AL. Okay, so using that we can solve and find what is the value of sigma. So we get sigma is equal to P by A plus or minus 2pH into E divided by AL plus P square by A square. Okay, all under the square root. Now this expression is very important, you have to learn this by heart. Okay, here also again we can see one more thing. I also already mentioned that impact loading is a special case of sudden loading. Only thing is, in sudden loading there is no h is equal to 0. Okay, so if you substitute h equal to 0, we have sigma is equal to P by A plus, this is 0, square root of P square by A square, which is again P by A, so 2P by A, right? So this was the case we obtained in the previous example, right? Also you can note that in this figure you can see that the h is very much higher than the deformation cost itself. Okay, so the work done is mainly contributed by the fall, which is your potential energy P into H. Okay, so if you neglect this delta L, okay, since delta L is very much, if you neglect the delta L, you can see that work done is equal to P into H, and work done, work stored in the bar is, which is strain energy, is sigma square into V divided by 2, right? So you can equate these two expressions to each other, okay, and get that in this case sigma is equal to square root of 2 EPH by AL. Okay, so this also has to be remembered and kept. Okay, now let's see a special kind of loading, which is shock loading. So let's assume that due to some kind of shock applied, there was a work done on the bar which was equal to U. So let's assume that shock is U. Okay, due to this there will be some deformation occurring in the bar, and there will be some resistance already offered, okay, because of which there will be some strain energy stored in the bar, which will be equal to half into R into delta L, okay, which again will be equated to sigma square by 2E multiplied by volume, which is A into L. Now we can equate work stored equal to work done. So u is equal to sigma square by 2e multiplied by a into l. We have sigma is equal to square root of 2u e divided by al. Now if you check here, this is analogous to the previous case, wherein in the previous case the work done was assumed completely as the potential energy which was due to fall, right? So instead of u we have pH there, okay? And if you check the final equation, instead of u again we have pH here, right? So this is something which is easy to remember and analogous to the previous example, okay? Now let's see a case wherein the applied axial load is varying along the length of the bar. So let's say that the member of length L and axial rigidity EA is subjected to a variable tensile force of P of x, which means that loading varies along with x. Okay, let's consider an element of length dx. Okay, let's say that the deformation of this particular small element is delta L. Okay, we already know that deformation is equal to PL by AE, right? So herein, however, P is equal to P of x and L, which is the length, is equal to elemental length, right? Dx divided by EE. Okay, we also know that delta L by dx, okay, deformation by original length will be equal to strain, which means that epsilon x is equal to px by ea, which is given here. Okay, also what is actually the strain energy? Strain energy is nothing but half into pfx multiplied by delta L. Okay, so half into pfx multiplied by delta L is again pfx dx divided by ee, which means that for elemental length strain energy is equal to half into px square divided by ea. Now in order to get the total strain energy, what you have to do is we have to integrate this elemental strain energy over the entire length 0 to L. So ux is equal to half into integral 0 to L p of x square divided by ea multiplied by dx. Okay, so if you substitute p of x as epsilon x multiplied by ea, we have this, we will get this expression as well. Okay, that's it for today's lecture. We'll continue more in the next lecture.